Students, welcome back. I'm Ncert, and today we'll continue with the Ncert actual exercise part 3 of chapter number 3, that is current electricity. Till now we had completed till question number 3.9, sorry 3.8. And today let's begin with 3.9. Determine the current in each branch of the network shown in figure 3.30. Okay, so now this is the given circuit. First, let's check whether the Resistor bridge is completed or balanced or not. If I take the ratio 10 by 5, that is 2, and on this side 5 by 10, 1 by 2. So no, the Resistor bridge is not balanced. So now let's say that the current flowing, current entering is I. So split up from in AB, let the current be I1, and in AD, let's name this point D. In AD, that will be I2. Okay, now let's take I1 current enters at point B, and from that, if I take that I3 is going in branch BD, then in BC it will be I1 minus I3. Okay, and at point D, the current entering from A is I2, from B is I3. So from D to C, it will be I2 plus I3. Okay, now at point C, the current coming are I1 minus I3 and I2 plus I3. So I3 gets cancelled. It will be I1 plus I2, and that is I. Okay, here there was current I, okay, towards A, and it's split in two parts, I1 and I2. So I1 plus I2 is I. Clear? Now to find out the current in each branch, we need to find out the value of I1, I2, and I3. So first, let's apply Kirchhoff's loop rule. Apply Kirchhoff's loop rule. Okay, so first to the loop A, B, D, A. Here, so see, from A to B, my journey and current is same, so minus IR, so minus 10 I1. From B to D, again it's in same direction, so minus IR, resistance is 5, so minus 5, and current is I3. And from D to A, direct my journey and direction of current are opposite, so plus IR, so plus resistance is 5 and current is I2. Reach back to point A, so this will be equal to 0. Here, taking minus 2 common, I will get 5I1, sorry, minus 5, let's take minus 5 common. So it will be 2I1 plus I3 plus minus I2. That is equal to 0, or else rearranging 2I1 minus I2 plus I3, that is equal to 0. Let's name this as 1. Okay, now let's take another loop. Another loop, we will take it as BCDB. Okay, so from moving from B to C, my journey and the journey of current is same. So minus IR minus 5 I1 minus I3. From C to D, again my journey and current, sorry, now my journey and current direction is opposite, so plus IR. So plus now 10, okay, and current is I2 plus I3. Here, now from moving D to B, my journey and direction of current are opposite, so plus IR, so plus resistance is 5 and current is I3, that is equal to 0. So minus 5 I1 minus plus 5 I3 plus 10 I2 plus 10 I3 plus 5 I3 is equal to 0. Okay, so minus 5 I1 I2 10 I2 I3 5 10 5. So this will be equal to 20 plus 20 I3 is equal to 0. Taking minus 5 common, I will get I1 plus not plus minus, because I'm taking minus 5 common, minus 2i2 minus 4i3 equal to 0. Clear? So I1 will be equal to 2i2 plus 4i3. Okay, so 2i1, that will be equal to 4i2 plus 8i3. Let's name this as equation 2. I have taken here 2i2 because I can rearrange equation 1. From equation 1, when I will solve further, I can get 2i1 minus, sorry, 2i1 is equal to i2 minus i3. Clear? And what is here? We get 2i1 equal to this. So I can write down, let's name this as equation 1 now. So from 1 and 2, I2 minus I3, that is equal to 4I2 plus 8I3. Clear? So 9I3, that will be equal to minus 5I2. Sorry, not minus 5, it will be minus 3I2. So I can get I3, that is, or I2 equal to minus 3I3. Okay, clear? Now putting this in 1, putting value of I2 in 1, I will get 2I1 equal to minus, here I will put minus 3I3 minus I3. So minus 4I3. So I1 will be equal to minus 2I3. Here, now applying Kirchhoff's loop rule again. Now to A, D, C, I will take this as EMF of the battery, that is epsilon A. Clear? So starting from A to D, opposite direction, sorry, same direction, A to D. So minus IR minus 5I2. From D to C, again same direction, so minus 10I2 plus I3. From C to now there is 10-volt battery. I am moving from negative to positive terminal, means plus. So plus 10. Okay. Now again the current is moving in this direction, same direction, minus IR minus 10. Now what is the current here? I, and I is equal to I1 plus I2. So I will write down I1 plus I2. Reaching back to point A, so this will be equal to 0. Minus 5I2 minus 10I2 minus 10I3. Let's take this minus 10 on the other side. So minus 10I1 minus 10I2, that is equal to minus 10. Clear? Now putting the value of I2 as minus 3I3. Okay? Or else first let's write down minus 5I2 minus 10I2 minus 10I2. So this will be equal to minus 25I2. Minus 10I3 minus 10I1. Minus 10I3 minus 10I1 equal to minus 10. Let's take minus 5 common. So it will be 5I2 plus 2I3 plus I1 equal to 2. Now let's put the value of I1 and I2 in terms of I3. So I2 is equal to minus 3I3. So this means that 5 into minus 3 minus 15I3. This I3 plus 2I3. And I1, that is again minus 2I3. So minus 2I3, that is equal to 2. So minus 15 plus 2, that is minus 13, or this will get cancelled. So I get I3 is equal to minus 2 by 15. And sorry, it's mistake. Here there is a mistake. It will be 2I1. Writing it once again. It will be plus 2I1. Now, 5, what is I2? 3I3, right? So 5 into minus 3, minus 15I3 plus 2I3 as it is. I1 is equal to minus 2I3. So minus 4I3 equal to 2. So minus 15 plus 2, that is minus 13, minus 4, minus 17. Minus 17 I3 equal to 2. So I3 is equal to minus 2 by 17. And got the value of I3. Okay. So now I3 is minus 2 by 17. That means I2. Okay. I2 will be equal to minus 3 into I3, that is minus 3 into minus 2, that will be equal to 6 by 17 ampere. And I1, that will be equal to minus 2 into I3, minus 2 into minus 2, 4 by 17 ampere. Okay, so let me write it down here. The value of I1, I got it as minus 4 by, sorry, 4 upon 17 ampere. I2 6 by 17 ampere, and I3 minus 2 by 17 ampere. It's negative sign because it's just because the direction is opposite. Okay. So now we need to find out the current in each branches. So I'm writing down the branches. Correct. So in branches it will be A, B, B, C, A, sorry, AB, AD, and BD. The other side, BC, DC, and I can write down here through C epsilon A. Clear? So this is the last one. Okay, so I can see here that in branch AB, okay, the current is I1. So what is the value? 4 by 17 ampere. In branch AD, I2, what is I2? That is 6 by 17 ampere. Okay, in branch BD, that is I3, so minus 2 by 17 ampere. This means that current flows from of 2 by 17 ampere from D to B. Okay, now in branch BC it's I1 minus I3. So what is I1? 4 by 17 minus I3. So I3 is minus 2 by 17, so plus 2 by 17. So 4 plus 2, it will be 6 upon 17 ampere. In branch DC, I2 plus I3. So what is I2? 6 by 17 plus I3, it means minus 2 by 17. So 6 minus 2, 4 by 17 ampere. And CEA, that is current I. And what is I? I equal to I1 plus I2. So that will be equal to 4 by 17 plus 6 by 17, that is equal to 10 by 17 ampere. Okay, so in branch A be 4 by 17, branch A is 6 by 17, branch B minus. You can use this like modulus. So I can write it down 2 by 17 ampere. Okay, 2 by 17 ampere. It's just the directions opposite. BC 6 by 17 ampere, DC 4 by 17 ampere, and CEA, that is 10 by 17 ampere. Clear? Okay, so note down question number 3.9. Now let's move to the next, that is 3.10. Question 3.10. A. In a meter bridge, the balance point is found to be at 339.5 centimeter. So in this question I can write down that L1 is equal to 39.5 centimeter. When the resistor Y is of 12 ohms, so Y, that is a standard resistance, that is equal to 12.5 ohm. Determine the resistance of X. So first let's solve this. Now here you can see that when there is no deflection, means at balance point, and balance point the Wheatstone bridge is balanced, so we will take the ratio X by Y equal to L upon 100 minus L. Here, so what is value of X? We don't know. Value of Y 12.5. L 39.5. 100 minus L means 100 minus 39.5. It will be 60.5. X is equal to 39.5 upon 60.5 into 12.5. Okay, so let's calculate it. 39.5 divided by 60.5 into 12.5. This is equal to 8.16. So the resistance X is equal to 8.16 ohm. Here, this was the first part. Now, one more question is asked: why are the connections between resistors in Wheatstone bridge or meter bridge made of thick copper strip? Okay, the reason why it used copper strips is that copper strip offers negligible resistance compared to this X and Y. Okay, the resistance of copper is very less. Right, so it will not interfere with the resistors that is kept in the gap AB and this BC. Clear? Now, second part B. Determine the balance point of the bridge if X and Y are interchanged. Means X is kept in Y position and Y is kept in this X position. Okay, then we will write down the ratio Y by X, that will be equal to L upon 100 minus L. Clear? So see, what is Y? That is 12.5. X 8.16, that is equal to L upon 100 minus L. So solving I will get 12.5 into 100, 1250 minus 12.5 L. This is equal to 8.16 L. So 1250, this is equal to 8.16 L plus 12.5 L. So this will be equal to 20.66 L. Okay, so L is equal to 1250 upon 20.66. So calculating it, 1250 divided by 20.66, this is equal to 60.50, right? So this is equal to 60.50 centimeter. Here, so the balance point is obtained at 60.50 centimeter from A. So you can see here that in previous case DC, this point DC was 60.50, this was 60.50. Now when you interchange the resistor, AD becomes 60.50. So just interchanging the resistors, L is interchanged. Yeah. Now see what happens if the galvanometer and cells are interchanged at the balance point. Remember, in this case, in both the case, the Wheatstone bridge is balanced. So in the other case also, galvanometer would not show any deflection. See, if I take the first figure, it's like this. Simplifying that figure, E, C, B, D. Between B and D, galvanometer. Okay. Now see, battery is connected between A and C. Clear? Okay, now Wisdom bridges balance, so galvanometer shows zero reflection. Okay, this is resistance between AB, BC, between DNC and END. Okay, now the question is interchanging the galvanometer and battery. Means see between point A, this is point A, not this, and point C. Okay, the battery is connected. So now just interchanging means the figure once again. A, B, C, D. Resistance between AB, BC, AD, and CD. Now between A and D, sorry, A and C battery was connected. Now let's connect it between B and D. Okay, so previously it was on BC arm galvanometer is connected, BD arm galvanometer was connected. Now on BD arm battery is connected, and between previously in BD arm, sorry, AC, between AC battery was connected. Now let's connect galvanometer AC. But say in this both the situation, if I take let's say R1, R2, R3, R4, this will be also same R1, R2, R3, R4. In this case, galvanometer shows zero reflection because R1 by R2, this was equal to R3 by R4. Right? Now just rearranging, I can get R1 by R3 equal to R2 by R4. Right, this shows that this system bridge is balanced. So again the galvanometer shows zero deflections. In both the cases the galvanometer will show zero reflection, so no current is flowing. Clear? So this was about question number 3.10. Just note it down. Now let's move to the next question, that is 3.11. 3.11, storage battery of EMF 8 watt and internal resistance 0.5 ohm is being charged by 120 watt DC supply using a series resistor of 15.5 ohm. Let's see, this is the battery EF having EMF equal to 8 watt. Series resistor, let's check this point A and okay, the internal resistance of the battery, that is equal to R equal to 0.5. Series resistor R is equal to 15.5. Now this is charged, so A and B both are connected by a 120 watt battery. Okay, so the charging takes place. Okay, now what is the terminal voltage of the battery during charging? Now see, when the battery is discharging, the terminal voltage is epsilon minus IR. But when the battery is charging, at that time the terminal voltage will be equal to epsilon plus IR because it is charging. Okay. So now see here. First the total potential. Here the battery, this battery is of 8 watt. Let's see that this is charged by okay 120 volt DC supply. Okay, so what is the effective EMF? That will be equal to 8 volt plus 20 volt. So I will write it down that okay, let's name this as V terminal volt. The effective V dash equal to 120 minus 8, that is equal to 112 volt. Why minus? Because see during charging both these batteries are connected with opposite polarity. Okay, so positive terminal connected to positive terminal, right? So as there is a higher volt, current flow in this way. Okay, so this is 112 volt and R equivalent, R and small r both are in series. So I will add it, 15.5 plus 0.5, that will be equal to 16 ohm. So the current flowing I will be equal to V dash by R equivalent, that will be equal to 112 divided by 16, and that will be equal to 7 ampere. Okay, so the terminal voltage Vt will be equal to 8 plus current is 7 and internal resistance 0.5. This is 8 plus 3.5, so that will be equal to 11.5 volt. This is the terminal voltage of the battery. Clear? Now one more question, what is the purpose of having a series resistor? Right, using series resistor we can control the current flowing, we can reduce the charging current, and as we are reducing the charging current we can reduce the heat loss I square RD. Okay, means heat loss in the form of internal due to internal resistance I square RT. Okay, so this was about 3.11, so just note it down. Now let's move to the next question, that is 3.12. 3.12, in a potentiometer arrangement, a cell of EMF 1.25 volt gives a balance point at 35 centimeter. If the cell is replaced by another cell and the balance point is 63 centimeter, what is the EMF of second cell? Okay, it's just very simple question, one mark question. The first cell is having EMF 1.25 volt. Okay, the null point L1 is 35 centimeter. Second cell EMF we need to find out. The null point is 63 centimeter. Okay, so we just in potentiometer for comparison of two cells, there is simple relation epsilon 1 by epsilon 2, that is L1 by L2, so that implies epsilon 2 is equal to epsilon 1 L2 upon L1. So 1.25 into 63 upon 35. So let's calculate. 1.25 into 63 divided by 35, it's 2.25 volt. Okay, so the EMF of the another battery or second battery is 2.25 volt. Sorry, it's 2.25 volt. Okay, so this was about 3.12. So just note it down. Now let's go to the next one, that is 3.13. 3.13, this is the last for the regular exercise of chapter number 3. Okay, the number density of free electrons in a copper conductor, estimate in example 3.1. Okay, you need to read example 3.1 for that question. Is 8.3 into 10 raised to 28 meter per meter cube. So N is equal to 8.5 into 10 raised to 28 per meter cube. How long does an electron take to drift from one end of the wire? 3 meter. L is equal to 3 meter to the other end. The area of cross section A is equal to 2 into 10 raised to minus 6 meter square. That is carrying a current of 3 ampere. Okay, we can directly solve it here. See, if the free electron drifts through a length L, then the drift speed, okay, drift speed Vd, that will be equal to L by T, right? And we need to find out the time. Now the relation between current density and drift velocity, J equal to NEVD. What was J? That is I by A, that is equal to NE. And what is Vd? L by T. We need to find out time, so T is equal to NELA upon I. Okay, so putting down the value, and that is number density 8.5 into 10 raised to 28. E, that is the charge of electron in Cauchy-Schwarz free electrons. So 1.6 into 10 raised to minus 19. L, length, that is given 3 meter. Cross section area 2 into 10 raised to minus 6 on current is 3 ampere. Okay, so let's calculate it. 8.5 into 1.6 into 3 into 2, so that is equal to 81 81.6 into 10 raised to 28 minus 19, that is 9. 9 minus 6, that is 3, divided by 3. So 81.6 divided by 3, that is equal to 27.2 into 10 raised to 3. So this will be equal to 27200 seconds. So the time it take will be equal to 27200 seconds. Clear? This was about 3.13. So just note it down. If you want, we can convert it into hour, that is 27200 divided by 3600. So that is equal to 7.5 hour, or you can also write it down 7.5 hour. Okay, okay students, so that's it for today. Here we have completed the regular exercise of chapter number 3. Thank you.